In this lesson, you will learn about evaluating limits analytically. First up, we discuss properties of limits. We learned in a previous lesson that the limit of f of x as x approaches c does not depend on the value of f at x equals c. But for some functions, this limit works out to equal f of c. So we can evaluate the limit using direct substitution to get the limit as x approaches c of f of x equals f of c. Now we will look at three examples where this behavior happens. First up, let's explore the constant function where f of x is equal to b. If we take a look at its graph, we know that it's a horizontal line where the y value of every point on that line equals b. Now let's look at the point x equals c, and it's easy to see that as x approaches c from both the left and right hand sides, the y value is approaching f of c, which is going to equal b. So this is a case where we can use direct substitution to get that the limit as x approaches c of f of x equaled f of c. Now, if we look at a linear function where f of x equals x, we take a look at its graph. If we fix a point at x equals c, once again, we see that the limit as x is approaching c from both the left and the right are both going to the same y value, which is that f of c equals c. So this is a case where we can use direct substitution to get that the limit as x approaches c of f of x equaled f of c. And finally, for a power function where f of x is equal to x to the n, and of course the shape of the curve will depend on whether n is even or n is odd, pick an x value of x equals c, and we look at the y values as x approaches c from both the left and the right, and they both approach the same y value where f of c is equal to c to the n. So this is a case where we can use direct substitution to get that the limit as x approaches c of f of x equaled f of c. Now we can use these results to make rules about basic limits. Let b and c be real numbers and let n be a positive integer. If we have a constant function, then the limit as x approaches c of b will equal b. For a linear function, the limit as x approaches c of x equals c, and for a power function, the limit as x approaches c of x to the n equals c to the n. In this example, evaluate each limit and name which rule was applied. Here, we have to evaluate the limit as x approaches 4 of 17. If f of x equals 17, then we know that we will apply the rule for the constant function. So if we apply this rule, then that means the limit as x approaches 4 of 17 will be 17. Next up, we have the limit as x approaches -2 of x cubed. So in this case, our f of x is equal to x cubed, which is a power function. So applying the rule for power function, we will do a direct substitution of c for x. So in our case, we have to take -2, plug it in for x, and we get -2 cubed, which is -8. Here, we have to evaluate the limit as x approaches pi of x. So our f of x is equal to x, which is linear. And the rule for a linear function is you take the value of c, do a direct substitution into x. So in our case, we have to take pi, substitute it in for x, and this limit will equal pi. Finally, we have the limit as x approaches -8 of 3 squared. So our f of x is equal to 3 squared. Now be careful not to make the mistake of thinking that this is a power function. Notice that the base of our exponent is not a variable, it's a constant. So our f of x is a constant function here. Then we apply the rule for the constant function, and this tells us then that the limit as x approaches -8 of 3 squared is going to be 3 squared, which is 9. Next, we explore some properties of limits. Let b and c be real numbers, and let n be a positive integer. And let f and g be functions with the following limits. The limit as x approaches c of f of x is equal to L, and the limit as x approaches c of g of x equals k. Now, if we have a scalar multiple, limit as x approaches c of b times f of x, remember that b is a real number, and when we have a real number constant multiplying the function inside the limit, we can pull it out front. This becomes b times the limit as x approaches c of f of x, which is equal to b times L. Because remember, this limit is equal to L. Here we look at a sum where we have the limit as x approaches c of the quantity f of x plus g of x, and that limit operation gets applied to both of those functions inside the parentheses. So this becomes the limit as x approaches c of f of x plus the limit as x approaches c of g of x, and we know both of those values. So this is going to equal L plus k. The same is true if we have a difference. So the limit as x approaches c of the quantity f of x minus g of x becomes limit x approaches c of f of x minus limit x approaches c of g of x. Once again, we know both of those values, L minus k. Here we look at the product, and we have limit as x approaches c of the quantity f of x times g of x, and this is the limit as x approaches c of f of x times limit as x approaches c of g of x. So you have to apply this limit to both factors in the product. We know that this first limit is L, and it will multiply this second limit, which is k. Next, we look at what happens when we have a quotient, and the limit as x approaches c of f of x over g of x becomes the quotient of the limits. So this is limit as x approaches c of f of x over the limit as x approaches c of g of x. And of course, the numerator equals L over the denominator, which is k. And as with any rational expression, the denominator cannot be 0. Now let's see what happens when there is a power and we have the limit as x approaches c of the quantity f of x raised up to the nth power. And we can write this as the quantity limit x approaches c of f of x, that entire quantity being raised up to the nth power. So this will equal L to the n. So one of the ways you can think about these rules is being able to say them in words. So the limit of a sum becomes the sum of the limits. The limit of a difference becomes the difference of the limits. The limit of a product becomes the product of the limits. The limit of a quotient becomes the quotient of the limits. And the limit of a power becomes the power of the entire limit. And now we can use all of these rules to help us simplify expressions involving limits. In this example, we have to evaluate each limit, given that the limit as x approaches -5 of f of x is 7, the limit as x approaches -5 of g of x is 12, and the limit as x approaches -5 of h of x equals 3. Here we have to evaluate the expression limit as x approaches -5 of the quantity 2f of x minus g of x over h of x. Now, using the quotient rule, we can rewrite this as the quotient of the limit as x approaches -5 of the quantity 2f of x minus g of x over the limit as x approaches -5 of h of x. So the limit of a quotient became the quotient of the two limits. Now we can do some further simplification in the numerator. So this becomes equal to, let's get our fraction bar in there. We have a difference, and we know the rule is that the limit of a difference becomes the difference of the limits. We also know that when we have a scalar multiple, that can come out front. And remember, the 2 only multiplies the part of the limit with f of x in it. So this can become 2 times the limit as x approaches -5 of f of x minus the limit as x approaches -5 of g of x. You have to be careful not to let the 2 multiply the g of x term. Now, in the denominator, we know that the limit as x approaches -5 of h of x is equal to 3. So we can go ahead and do that substitution. Let's continue to simplify. Make the fraction bar. Now we have 2 times This limit, as x approaches negative 5 of f of x, we know is equal to 7. And we have to subtract the limit as x approaches negative 5 of g of x, which we know is 12. We still have 3 in the denominator, and this is going to simplify. In the numerator, we have 14 minus 12, which is 2 over 3. And this is our simplified result. Next up, we have to evaluate the limit as x approaches negative 5 of the quantity h of x to the third power. So we will use the power rule to rewrite this as the quantity limit as x approaches negative 5 of h of x, that whole quantity raised up to the third power. Now that we have this exact limit expression, we can replace that with 3. So this will equal 3 to the third power, which simplifies to be 27. We continue to study limits of functions. First, we will explore more functions where we can find a limit using direct substitution. Let c be a real number. The following limits can be evaluated using direct substitution. If we have a polynomial function, p of x, then the limit as x approaches c of p of x is equal to p of c. And this was done by direct substitution, where we take the value of c and plug it in for x. If we have a rational function, r of x equals p of x over q of x, then the limit as x approaches c of r of x is equal to r of c, which equals p of c over q of c, where q of c cannot equal 0. And so again, the direct substitution was that we took our value of c and plugged it in for x. If we have a radical function and we let n be a positive integer, then the limit as x approaches c of the nth root of x will equal the nth root of c. Now note, if n is even, so we are taking an even root, then this limit will exist only if c is greater than 0. We know that we cannot plug negative numbers into a root which has an even index. If n is odd, then c can be any real number. And in this limit, we evaluated it using direct substitution by taking the value of c and plugging it right in for x. In this example, we have to evaluate the limit as x approaches negative 1 of x squared minus 1 over x minus 1. Because we have a rational function, we know that we can evaluate this using direct substitution. So this becomes negative 1 squared minus 1 over negative 1 minus 1 in the denominator. This is going to equal, simplifying the numerator, we get 1 minus 1, which is 0. In the denominator, we have negative 1 minus 1, which is negative 2, and 0 over negative 2 equals 0. In this example, we have to evaluate the limit as x approaches 5 of the cube root of negative 32 plus x. Because we have a radical function, we know that we can use direct substitution to evaluate the limit as long as we don't violate any issues with the domain. So if we take this 5, plug it in for x, we get the cube root of negative 32 plus 5, which equals the cube root of negative 27, which is equal to negative 3. And remember, it's okay to have a negative under a radical when the index of the radical is an odd number. Here we learn how to find the limit of a composite function if f and g are functions such that the limit as x approaches c of g of x equals L, and the limit as x approaches L of f of x equals f of L, then the limit as x approaches c of the composite function f of g of x will equal f of the limit as x approaches c of g of x. And remember, we said that this limit is equal to L, so then that means we can replace limit as x approaches c of g of x with the value L, and this becomes f of L. Let's take a look at an example to understand how this works. Here, we are given that the limit as x approaches 1 of p of x is equal to 3. The limit as x approaches 3 of q of x is equal to q of 3, which equals 10. We have to evaluate the limit as x approaches 1 of q of p of x. So this is our composite function here, q of p of x. Now let's apply this rule right here. We know that the limit of a composite function means that I can take the outer function of the limit of the inner function. So that means in our example, we can take the outer function, which is q, of the limit of the inner function. So limit as x approaches 1 of p of x Now we can start evaluating from the inside out. We have q of the quantity, limit as x approaches 1 of p of x, that was given. We know that it's equal to 3. And now we know that q of 3 is equal to 10. And this is our result. Next, we find a trig function limit using direct substitution. Let c be a real number in the domain of the given trigonometric function. Then limit as x approaches c of sine of x equals sine of c. So here is where we are doing the direct substitution. And you can see that that's true for each of the 6 trig functions. As long as c is in the domain of the trig function, then to find the limit as x approaches c, we are going to do a direct substitution by putting c in for x in every case. In this example, we have to evaluate each limit. We are given the limit as x approaches pi over 3 of sine squared of x. So doing the direct substitution, we know that this will equal sine squared of pi over 3. Now remember that this notation is just shorthand for saying take the quantity sine of pi over 3 and square it. Now referring to the special angle chart, go to the sine row and over to the pi over 3 column. We know that the sine of pi over 3 is rad 3 over 2. We have to square that. Radical 3 squared is 3, and 2 squared is 4. So our result in simplest form is 3/4. Next, we have to find the limit as x approaches 5 pi over 4 of tangent x. So we need to do the direct substitution, and we get tangent of 5 pi over 4. We know that 5 pi over 4 lives in quadrant 3. The reference angle is pi over 4. And from the special angle chart, we go to the tangent row, over to pi over 4, and that value is 1. And in quadrant 3, tangent is positive, so this just equals 1. Here, we have to find the limit as x approaches 2 pi over 3 of x cosine x. We can do a direct substitution and make sure that you put the 2 pi over 3 in for both of those x's. So we will get 2 pi over 3 cosine of 2 pi over 3. So this becomes equal to 2 pi over 3 times, we know that 2 pi over 3 is going to live in quadrant 2. The reference angle is pi over 3. So if we look at the special angle chart, we go to the cosine row, over to the pi over 3 column, and we find out the value is 1/2. Now in quadrant 2, we know that cosine is negative, so cosine of 2 pi over 3 is going to be negative 1/2. Now when we simplify, the 2 in the numerator here will cancel with the 2 in the denominator here, and our result in simplest form is negative pi over 3. In section 3, you will learn techniques for finding limits. First, a quick algebra review of functions that agree at all but one point. If f of x equals g of x everywhere except at x equals c, we say that f and g agree at all but one point. To understand this, let's look at an example where we have to write a simpler function, g of x, that agrees with the given function at all but one point. Here we have f of x equals 2x squared minus 7x plus 3 over x minus 3. Now what we can do is factor the numerator, and we know that to get 2x squared, we will need 2x times x. To get a plus 3, we can have 1 times 3 or negative 1 times negative 3. And since the middle term is negative, we need the 1 and 3 to both be negative. Now to get the negative 7, we need the minus 3 to be here and the minus 1 to be here. Now you should always double check your factoring by using the FOIL method. First times first gives us 2x squared. Outer times outer gives us negative 6x. Inner times inner gives us negative x. Those two combine to be negative 7x. And last times last gives us the plus 3. Let's get the fraction bar in there. Bring over the denominator. Now notice that this rational expression has a common factor in the numerator and the denominator. Now we cannot cancel this factor in the function f of x, but what we can do is write a simpler function, g of x, let that equal 2x minus 1, and now g of x will agree with f of x everywhere except at x equals 3. So notice that f of 3, if we tried to plug in x equals 3 into f of x, the denominator would equal 0. So f of 3 does not exist. Whereas g of 3 does exist. We can plug a 3 in for x here. 2 times 3 is 6, minus 1 is 5. So at x equals 3 is the only place where f of x and g of x will not agree. Any other value of x that we plug in to f of x and g of x will output exactly the same value. So g of x is the simpler function that agrees with f of x everywhere at all but one point. And in this case, that point is at x equals 3. Now we will use these simpler functions to help us evaluate limits. Now you will learn a technique for how to find a limit by factoring and canceling. If limit as x approaches c of f of x cannot be found directly, but f of x equals g of x for all x not equal to c in an open interval containing c, and the limit as x approaches c of g of x exists, then the limit as x approaches c of f of x equals the limit as x approaches c of g of x. Now the reason this works is because we're going to find a simpler function, g of x, that agrees with f of x everywhere except at x equals c. And since the two functions will agree everywhere except at c, then their limits will have to agree as well. Because remember, in the limit, we look at points getting infinitely close to c without actually equaling c. Let's look at an example to see how this works. Here, we have to find the limit as x approaches negative 2 of x squared minus x minus 6 over x plus 2. The first thing we always try is direct substitution, because if that works, then we've found our limit and are finished. So let's see if that will work in this case. Plugging in x equals negative 2 into the numerator, we have negative 2 squared minus negative 2 minus 6 over, in the denominator, we will have negative 2 plus 2. So this becomes 4 plus 2 is 6 minus 6 is 0 over 0. Now 0 over 0 does not equal 0. Be very careful. This is equal to undefined. This does not exist. So let's make a note that this limit cannot be found directly. And what we've discovered is when that happens, if we are able to find a simpler function, g of x, that will agree with f of x everywhere except at c, then we can find the limit as x approaches c of f of x by doing the limit as x approaches c of g of x. So now let's write this as the limit as x approaches -2. We need to factor this numerator, and this is a pretty simple one. To get x squared, we will take x times x. To get -6, we have a couple choices of using 3 and 2 or 1 and 6, and we know one factor will need to be positive, the other will be negative. Since we need a negative x for the middle term, we know that this will factor to be x plus 2 times x minus 3. Let's get the fraction bar in there. The denominator of x plus 2 is still there. So now, if we were to write a simpler function that agrees with the given function at all but one point, we could say that g of x is equal to x minus 3. Now we know that in the function, we would not be allowed to cancel out this common factor of x plus 2. But we know that we can use the simpler function to evaluate the limit, and so we are allowed to cancel out the common factor in the limit. And this becomes the limit as x approaches -2 of x minus 3. And once you simplify, then always your next step will be to try direct substitution again. And if we plug this -2 in for x, we have -2 minus 3, which is -5. And now let's make sure you're crystal clear on what happened here with these limits. This is the limit as x approaches c of f of x, and this is the limit as x approaches c of g of x. And we used the limit of this simpler function to help us find the limit of the more complicated function. And the reason we had to do that was because we could not use direct substitution to find the limit of that more complicated function. So by finding this simpler function, we were able to evaluate its limit, which was -5, which is going to be equal to the original limit. In this example, we have to find the limit as x approaches 0 of 2x over the quantity x minus 4x squared. The first thing we always try is direct substitution. If we put 0 in the numerator, we get 2 times 0 over, putting 0 in the denominator, we get 0 minus 4 times 0 squared. This becomes 0 over 0, which we know is undefined. So this limit cannot be found directly. That is always going to be our signal that we need to find a simpler function that agrees with our original function and use it to evaluate the limit. So this will equal the limit as x approaches 0 of 2x over, the denominator can be factored. If we take out an x, then we would have 1 minus 4x. So now we can write a simpler function that agrees with the given function at all but one point. Our g of x is going to equal 2 over 1 minus 4x. Even though we can't cancel the x in the original function, we are allowed to cancel it in the limit. So this becomes the limit as x goes to 0 of 2 over 1 minus 4x. And as soon as you simplify, the next thing to try is direct substitution. This is equal to 2 over 1 minus 4 times 0, which simplifies to 2 over 1, which is 2. And so to find the limit of this more complicated function, we were able to use the limit of the simpler function because our g of x agrees with the original f of x everywhere except at x equals 0. In this example, we have to find the limit as delta x goes to 0 of the quantity x plus delta x squared plus x plus delta x minus 5 minus the quantity x squared plus x minus 5, that whole thing over delta x. Now, as always, the first thing we would try is direct substitution. And if we put in 0 for delta x in this first term, it would be x squared. If we put 0 here for delta x in the second term, we would get a plus x. Then we have that minus 5. And now if we distribute this negative sign over the three terms here, we would get minus x squared minus x and plus 5. And that whole thing has to be over delta x, which we would be substituting 0 there too. Now in the numerator, everything cancels. We've got an x squared and a minus x squared, an x and a minus x, a negative 5 and a plus 5. So this is 0 over 0, which we know means it does not exist. So now that is our signal that we need to find a simpler function for this big complicated thing, and we want to use that simpler function to find the limit. So let's see what happens here. This is equal to the limit as delta x goes to 0. And now we need to expand out this numerator here. For this first term, we would get x squared plus 2x delta x plus delta x squared. For the second term, we just have plus x plus delta x. Then we have that minus 5. And now be careful to distribute this negative sign right here to all three of these terms. That's one of the most common errors that happens in limits, is people forget to distribute that negative sign. So we will get minus x squared minus x and plus 5. All that has to go over our denominator of delta x. Now let's see what we can simplify. We've got an x squared that'll cancel with a minus x squared. We have a plus x here that will cancel with a minus x here. And we have a minus 5 and a plus 5 that'll cancel there. So let's bring down our equal sign, and the limit as delta x goes to 0. A quick reminder that you need to keep writing this limit operation until we actually perform the limit. Now, as we look at this numerator, we notice that every term in the numerator has a delta x in it. So let's go ahead and factor out that delta x. We've got delta x times 2x plus, from this term, we would have a delta x left, and from this term, we would have a plus 1. Put in the fraction bar. Our denominator of delta x is still there. Now we can simplify this to be the limit as delta x goes to 0. Now remember, in the limit, we are allowed to cancel out these common factors. So we will cancel out this delta x with this delta x, and we will be taking the limit of 2x plus delta x plus 1 as delta x goes to 0. So now this is our simpler function. Our g of x is equal to 2x plus delta x plus 1. Now that we have the simpler function, we're going to try direct substitution again. And when we do this direct substitution, that means we are actually taking the limit. So now for the first time, we don't have to write the limit notation anymore, because in doing the direct substitution, we have performed that operation. So if delta x goes to 0, then that means we have 2x plus 1. And this is our result in simplest form. And once again, we applied this property where if we cannot find the limit of a function directly, but we are able to find a simpler function that agrees with that original function everywhere except at the value of c, in this case 0, then we can use that limit to find the limit of the original function. In this example, we have to evaluate the limit as x goes to 0 of the quantity 1 over x plus 4 minus 1/4 over x. Now, if we try direct substitution, and remember that's always the first thing we want to try because it's the simplest thing, we take that 0, we put it in for x, and we would get 1/4 minus 1/4 over 0, which is 0 over 0, which of course is undefined. Now, as soon as we get a result of undefined with the direct substitution, that tells us that we will need to look for a simpler function and use that simpler function to find the limit. Now, from your college algebra class, You learned that when you had a complex fraction, what you want to do is multiply by 1 in the form of the least common denominator over itself. So between x plus 4 and 4, our LCD is 4 times x plus 4. And remember, we can only multiply by 1, so we have to put that in the denominator as well. Now, this is equal to the limit as x goes to 0. Let's get our fraction bar. Now be careful. We need to multiply numerator times numerator, and we will need to distribute this to both terms of the numerator. So when we take 1 over x plus 4 and multiply it times 4 quantity x plus 4, that's going to become 4. Then we have the subtraction symbol. And when we take 1/4 and multiply it times 4 quantity x plus 4, we are left with quantity x plus 4. Then we have to take denominator times denominator, and we get 4x times the quantity x plus 4. Something to be very careful of here, a mistake to avoid, these x plus 4's right here do not cancel because this is over a subtraction in the numerator. If this numerator was 4 times the quantity x plus 4, then you could cancel those common factors. So now let's simplify. This is equal to limit as x goes to 0. In the numerator, we have 4 minus x minus 4. In the denominator, 4x quantity x plus 4. This is equal to limit as x goes to 0. In the numerator, those two 4's will cancel, and we have negative x over 4x quantity x plus 4 in the denominator. And notice we're having to write limit as x approaches 0 every time here because we have not performed that limit operation yet. So limit as x approaches 0. Now, within the limit, we are allowed to cancel that common factor, and this simplifies to be negative 1 over 4 times the quantity x plus 4. Now here is that simpler function that we're going to use to find the limit. So we know that negative 1 over 4 quantity x plus 4 will output all the same values as our original function, except at x equals 0. So now we can go ahead and perform the limit with a direct substitution, and this is going to equal negative 1 over 4 times 4, because when we put a 0 in for x, this quantity becomes 4, and this simplifies to be negative 1 over 16. So this is our result in simplest form. In this example, we have to find the limit as x approaches negative 1 of quantity x cubed plus 1 over quantity x plus 1. We start with direct substitution. So we have to put in negative 1 for x in the numerator So we get negative 1 cubed plus 1 over, putting negative 1 into the denominator, we get negative 1 plus 1. Simplifying, negative 1 cubed is negative 1, plus 1 is 0, over the denominator, which is also 0, and this is undefined. So because we cannot evaluate the limit directly, we will need to work on finding a simpler function and use that to evaluate the limit. So now this will equal the limit as x approaches negative 1. Now from our algebra class, we know that expressions in the form of a cubed plus b cubed can be factored into the quantity a plus b times the quantity a squared minus ab plus b squared. So the numerator will become quantity x plus 1 times the quantity x squared minus x plus 1. In the denominator, nothing to factor, so we just bring over the x plus 1. Now we know that in the limit, we are allowed to cancel out this common factor, so this will equal limit as x approaches negative 1 of the quantity x squared minus x plus 1. And now this is the simpler function that we will use to calculate the limit. We know that x squared minus x plus 1 will output all the same values as our original function of x cubed plus 1 over x plus 1, except at x is negative 1. So now, to evaluate this limit, we will do a direct substitution, and this will equal negative 1 squared minus negative 1 plus 1. And notice that we did not write the limit operation anymore, because by doing this direct substitution, we are performing this limit. So here, this will simplify. This is 1. This becomes plus 1. So that's 2 plus 1. We get 3. And this is our result in simplest form.